Oh, I need to share my screen on Zoom. Okay, today we're going to talk about dot products and orthonormal vectors. This is the second lecture related to chapter 9 of the book. We will have another lecture next week, and that will basically finish chapter 9. Our objectives are still learning more about vector spaces and more abstract view of them when we are dealing with high-dimensional problems. And okay, now it's maximized. And today we are going to cover a very important process in linear algebra called Gram-Schmidt process. This is a way to generate a set of orthonormal vectors or bases. And we're going to look into what do we mean by a set of vectors being orthogonal or normalized or orthonormal. And that's the topic of today. And then we're going to generalize it to matrices from vectors. So the first thing we need to cover is dot product. Many of you probably have seen dot product before, and maybe you've been waiting for it to show up at some point. We never talked about it. Today, finally, we're going to cover the dot product. So the definition of dot product in Rn is, if we use this notation, a very big dot to differentiate it from matrix product that sometimes we use dot. It is just the sum of multiplication of corresponding elements of two vectors of the same size. Now, another name for dot product is inner product. Inner products are more general. Dot product is a special case of inner product. A lot of time, I will probably use inner product. You can use both. Whatever is your preference is fine. From the context, when I say inner product, you know I mean the dot product. Now, if you look a little closer, we recognize that the dot product is actually something that we've seen before. Instead of the summation notation, we can just say one vector, one of them transpose times the other vector. This will, in fact, give us the same thing, because U transpose times V as vector-vector multiplication, it will result in sum of the multiplication of their corresponding entries. So you could actually take this as a definition. You could say the dot product is defined as U transpose. Dot product of U and V is defined as U transpose times V. Another notation that I personally like is using these angled brackets. So it really doesn't matter which one you use. All of them are equivalent. It's like naming water in 10 different languages, right? It doesn't change the fact what you mean. You can invent another notation. That's fine. We're not going to use it, but you're free to do that. But the transpose version is particularly attractive because it's just vector multiplication. We've seen it before. And in fact, we used it to define the norm, if you remember. So that's the dot product or inner product of two vectors. Yes, Jess is pointing out that we use this in the grad version of Rob 101, which is called Rob 501. One day, maybe we see you there. Who knows, maybe I teach it by the time you're taking 501. Right now, I'm not teaching it. Maybe you're unfortunate enough to meet me again in 501. So we use this notation in a lot of grad courses and more advanced math because it can be used for more general definition of inner product too. But we leave it to your preference. Now this was purely algebraic definition. We did not give it any meaning. That's just defined as a dot product. When we define the Gram-Schmidt process, I'll give you a little intuition. But we can talk about it outside of the lecture as well. You can give it geometric meanings as well. But we're using the algebraic definition for now. An example, compute the dot product of u and v. What should I do? Tell me, I write the answer. So I can use this, right? You wanted to use the other version. It's going to be 1 times 2 plus 0 times 4 plus 3 times 1. You could write using the summation notation. We only have 3 elements. So it's going to be u1, v1 plus u2, v2 plus u sub 3, v sub 3. It will be the same, right? So it's not very challenging. Dot product of two vectors, you've done way more complicated calculations by now. And if you remember matrix multiplication, in the general formula, if you go back all the way to the very beginning lectures, when we had the general matrix multiplication, each of the entries of matrix had this form, this summation. So that's interesting that we were in fact doing dot product of rows and columns to construct the matrix multiplication. Just to make you curious, you can go back and look at it, and then you should recognize that, oh, these are just dot products of rows and columns. That's related to matrix multiplication. The first, the standard multiplication. Okay, so whatever convention you use, you get the same answer, not surprisingly. What about these two? Can you do it with your mind? 1 times 0 plus 0 times 1 plus minus 1 times 0 plus 0 times 1. It's always 0. This was a 4-dimensional example for you. Do you have any question? I assume you're comfortable with that, but if you want me to explain more on the dot product and the definition, we can talk more about it. Okay, sounds like you're comfortable with it. So what is the use of dot product? What is it good for? We define that, and obviously we define things when they have a utility. Otherwise, it will just make it cluttered with all the definitions. So the inner product is a generalization of the right angle, 90-degree angle, between two vectors in Rn. For 2D, it is convenient to draw two vectors and say they are orthogonal. That means they form a right angle. Orthogonal right angle means they are pointing out to completely different direction in the space. They have nothing in common, right? There is no way by following W1 you can end up in the direction of W2, right? You can, intuitively you can imagine that's never going to happen. If you move along one of them, you will not move along the other one. Now, this definition of inner product was very general. It was for Rn, vectors of any dimension. And it will allow us to generalize the notion of orthogonality, the right angle. We say two vectors in Rn, W1 and W2, are orthogonal. This notation means they're orthogonal. If and only if their dot product is 0, using whatever notation you would like to use. So if I give you two vectors and ask you, are they orthogonal? You calculate the dot product. If it's 0, you know they're orthogonal. For example, if I can say 1, 0, it's dot product with 0 and 1. Now, clearly, whenever one of them has 0, right, the other one has a number, and this will result in 0. They have nothing in common. Now, this is a very nice case because this is, in fact, the example I gave you. If we define our standard 2D plane, but it doesn't have to be 0 and 1. They can have any, what about V1 and V2? Then they're not 0. They're just any arbitrary numbers in the space. Then imagine a 100-dimensional space. You have 100 numbers. We can't visualize. We want a way to know what's the angle between them. Are they orthogonal or not? So the dot product enables us to test that. So it generalizes our idea, intuition of orthogonal vectors to higher dimensions. For example, here we have two vectors, W1 and W2. They are not aligned with usual x and y axis in 2D. So one of them is 3 and 4. The other one is negative of 7 over 3. The other one is 7 over 4. You take the dot product, it's 0. That tells us these two vectors are orthogonal. It is not easy at all by looking at them saying that these two are orthogonal. I cannot do that. I don't think that's a very easy thing to do. Yeah?
Are we also going to learn about using the dot product from the angle between two vectors, or is this not?
The question is, are we going to talk about the angle between two vectors? I think at some point, but not today. We don't need it for today. We need the notion of orthogonality. I think in one of the lectures when I talk about hyperplanes towards the end of the course, we talk about that. But it is something that we can define using the dot product. Maybe you've seen the familiar formula of right? I think it's something like that. We don't talk about it, but that's true. You can take the angle of between two vectors using the dot product. Now this is dot product. I use the more general notation. But don't worry about it. We don't need it right now. So this is very useful, and even for the 2D example, it's non-trivial to look at the numbers. You can draw it, of course, but for 4 dimensions and above, you can't draw it. So we rely on algebraic tools to examine orthogonality. Let's look at a classic theorem, Pythagorean theorem. Came up a few lectures ago, I think. Now the theorem says that suppose W1 is orthogonal to W2. Then we have the norm squared of W1 plus W2. The norm squared of sum of two vectors equals norm squared of their individual vectors. This definition holds for Rn, any dimension. The classic one is for, what you saw probably in high school is for 2D. Now, this is again only true if two vectors are orthogonal. How should we prove it? Imagine you're living in ancient Greece and you want to compete with Pythagorean, you want to improve the Rn version of it instead of R2. Somehow you know from the future yourself in the future that orthogonality is something that is given to you.
Is it like you do on the left inside of the bars and square W1 plus W2 all the way to Wn squared equals, and then W1 squared plus W2 squared plus all the way to Wn?
You are saying that if I have W3, it is still true, assuming all of them are orthogonal, right? Yeah, you can generalize it, but just for these two, if you want to prove it. Taking a ruler and measure it, that's too hard. We're going to be really bad at measuring ourselves. We want a perfect proof, no error in measurement. So a lot of time, proofs can be done by direct calculation, right? Not always you need a very complicated idea to prove something. We can directly calculate left-hand side, and if we get right-hand side, then it's true, right? That's just sometimes you can prove some identities like this. Now for that, we're going to rely on the fact that the norm square of V is V transpose times V, right? Norm squared. We also going to rely on the fact that generally vectors or matrices A plus B transpose is A transpose plus B transpose. Now, we know these are true from previous lectures. So what we're going to do, we are going to first, using the assumption, establish that given that W1 is orthogonal to W2, then their inner product must be 0. So whenever we see W1 transpose times W2, or W2 transpose times W1, we know that that's going to be 0. And we talked about the norm squared. It's going to be V transpose times V. Now, given that, let's expand the left-hand side. It's going to be W1 plus W2 transpose times itself, times, W1 plus W2. Bring the transpose inside, right? And then distribute it. And once you distribute it, it's going to be W1 transpose times the sum of them plus W2 transpose times the sum of them. Distribute it again, you're going to get the norm of the, right? The first vector, and all the cross terms, W1, W2 terms, are 0 because they're orthogonal using the property of the dot product. And then second one here. So just because they're orthogonal, all the cross terms end up being 0, and that's how we get this theorem. It is just a consequence of orthogonality and dot product, the property of the dot product. Okay, I see no questions. Moving on. I give you 3 vectors. Tell me which pairs of vectors are orthogonal. What's the starting point? I always ask what's the starting point because that's the hardest part. If you know where to start, you just carry out some calculation, usually end up somewhere better than where you started.
We could start from transposing U and then find the dot product of U transpose and U.
Great, yeah. That's a great idea. So let's transpose, let's say U, and then follow the definition of inner product and see what we get. Now, if you want to know U and V are orthogonal or not, we have to do it separately, right? If you want to know U and W are orthogonal or not, we have to do it separately. And we probably want to know if V and W are orthogonal or not. Now, you don't need to do both of them because by definition, they're the same. So we calculate these, and whichever is 0 indicates that the 2 vectors are orthogonal. If you carry out the calculations, it turns out U and V are orthogonal, V and W are also orthogonal, but U and W are not orthogonal because the results of the dot product, it's negative 11. Right? So dot product can be negative 2. But you know that the dot product of a vector by itself, it cannot be negative because that was the definition of norm squared. We would take a square root of that, right? But if you take in 2 different vectors, it can end up being negative. Okay, so our conclusion is that U and V are orthogonal, U and W are not, and V and W are orthogonal. Great, we got the good, correct answer in chat too. I think all of you are following. I think we established what is the dot product, what is it good for, and how we can use it to solve some problems. Now, we want to define the notion of orthogonality and orthonormality for a set of vectors. So a set of vectors, V1 to Vn, is orthogonal if for every pair of them we have their dot product is 0, right? If you have 10 vectors, we say the set of vectors is orthogonal if every 2 of them basically are orthogonal with respect to each other. So when you pick an arbitrary pair of vectors, I and j, from that set, V1 to Vn, what we get is that their inner product is 0. Then we say the set of vectors is orthogonal. So this definition is useful because then when I say that, imagine or suppose we're given a set of orthogonal vectors, right? Then you know that each pair has a 0 dot product. I don't have to write it. By definition, we know what it means. What about orthonormal?
Is it possible to have, like, if you're dealing with some space Rn, you can't have more than n orthogonal vectors, right? Because then, like, it's not possible, right?
Yeah, good question. So let's make it even simpler, right? R2. So you're asking, in a space like R2, can I have 3 orthogonal vectors? From the look of it, we can't, right? Because there's 2, yeah? Yeah, a scalar multiple of a vector, let's say this is V1 and V2. It's just another, I don't know, you can call it V1 bar. It is still the same direction. It's not going to change the direction, even if it's negative. Now, from the previous lecture, we learned that the span of these vectors, right, will be the set of all linear combination of them. Now, if you have 2 vectors, even not orthogonal, right, in R2, set of 2 vectors, you can cover the whole space with their linear combinations. And why we can do that, because it's really informally, because you can move to any point, right, in this space by linear combination of these 2 vectors. If they're orthogonal, it makes it nicer to work with. We like that because we have an idea of independent directions in the space. Otherwise, they're not independent. We like that because it's cleaner. So for Rn, we cannot imagine it that easily, but given that we can verify this R2 by algebra and it generalizes to higher dimensions, then probably with n independent directions, we can cover the span of the n independent vectors, linearly independent, will cover the whole space, right? Then any other vector will be linear combinations of them. Does that answer your question? In mechanical system or physical, you might call them degrees of freedom, right? How many degrees of freedom you have to move in a course on mechanics and mechanism, you'll hear this. We have Rob 103, robot mechanism. I don't know if they cover it, but it's very likely that they talk about it. So you can already see that a lot of algebraic intuition will make other courses, other engineering notions very relatable, because you already understand a more abstract version of it. Realization is always easier to understand than the abstract version. Okay, so the next thing is orthonormal. A set of vectors is orthonormal because if, first of all, they are orthogonal and they are normalized. That means the norm of each vector is 1. It has unit length. Yes, go ahead.
Would it get a set of unit vectors in the directions of R?
I'm not following your question. Can you rephrase it?
Would the set of orthogonal vectors just be a set of unit vectors, like ijk?
Yeah.
R3, would they be orthogonal?
Okay, yeah, I give you an example. That's, yeah. I'll learn your name. I can say it. Yash says that, can we give ijk in R3 as an example? Yes, we can. So the general definition here is that they're orthonormal. Orthonormal is a shortened version of orthogonal plus normalized, right? So first they should be orthogonal, then they should be normalized. Why normalized? Because unit length is easy to work with. It's, in a sense, it's a natural choice. It's not going to rescale if you use it as direction, just like the columns of the identity matrix. It's a natural choice. In 2D, we had I and j, for example, right? I was 1 and 0. This is very common in physics. Sometimes in math too, but mostly in physics. In 3D, we can have x, y, z. And you can have I, j, k. Now, it is true that I, j, k form a set of orthonormal vectors because every two of them, you can try, the dot product is 0, and the length of it, the norm of it, is also 1. So in fact, this I, j, and k will give you a set of orthonormal vectors. Later in chapter 10, we will call them bases. It's a more advanced way of thinking about them. And it's related to that idea of spanning the space. So take this as an example. This R2 and R3 is an example of, I write k here, 0, 0, 1. What about the four-dimensional space? What letter you would use? G? T. Is that for space-time? What about R5? What's the fifth dimension? Time is the fourth dimension in physics. What do people do in the string theory? They have, I don't know, 70, 80 dimensions? So we decided to systematically opt for E1, E2, E3, right? So we don't have enough alphabets to keep everybody happy like this. Okay, so we covered orthogonal and orthonormal set of vectors. How to normalize a vector. Is that easy or hard? Yes. Emily's idea is to divide by norm. So in a sense, it's easy, but it is actually hard if it's a long vector. Nobody wants to calculate the norm. So you will use Julia to do it. So if we calculate the norm, here's an idea. Now, if the norm of W is some number like alpha, right? If we calculate something like W tilde, divide W by its norm, this should result in a unit norm. And you can verify that, take the norm of this new vector, right, which is W divided by alpha, given that alpha is not 0, right? Do not normalize a vector if the norm is 0. That means the vector is the 0 vector, right? Then the norm will be 1, and that's what we do here. So the norm of W is square root of 26, whatever number it might be. Divide each entry by the norm. Then you can verify in Julia that if you take the norm of this new vector, W tilde, it is normalized. So to normalize a vector, we divide by the norm of the same vector. Then it will be a unit vector. Now, given an orthogonal set of vectors U and V, how to make it orthonormal? An orthonormal set. We're just building up the terminology, making it more complicated, using the definitions to get used to what we defined. So, orthogonal set, we just defined that. That means U and V have a 0 dot product. Their dot product is 0. For a set to be orthonormal, every pair of vectors must be orthogonal, and each vector must have a unit norm. So given our previous example, what we can do, we can take the norm of each vector, calculate the norm of each vector, and then divide each vector by its norm, then your set will be orthonormal. So you can always convert a set of orthogonal vectors to orthonormal, right? Seems doable. Now you might ask how to get orthogonal vectors, a set of orthogonal vectors. That's the reverse process, right? I give you orthogonal vectors and I say normalize it, that's all good. What if I give you a set of vectors and I ask you, give me a set of orthogonal vectors. Or I could say orthonormal vectors, but you can normalize them always. How to do that? That's the reverse process. It's not. Is it obvious how to do it, or it's not? A few centuries ago, probably there was a prize for this. Not anymore. But we're buying ideas still. If you have any ideas how to do it. Now, it's not obvious. We need a systematic algorithm to do it. And that's the Gram-Schmidt process that we're going to talk about it today. So Gram-Schmidt is really the reverse version of this. I give you a set of vectors. I want to convert it into a set of orthogonal or orthonormal vectors. Gram and Schmidt, two different people. It's named after them. I don't know who orthogonalized and who normalized, but both of them together apparently made the algorithm. Although Wikipedia says that Laplace was aware of it much earlier and was using it.
What's the problem? Are we trying to turn that into a...
Okay, Yash is asking, what's the problem? That's always good to ask, what's the problem? The problem is that I give you a set of vectors and I ask you somehow make this set to be a set of orthogonal vectors. That means, by the definition we had, every pair of vectors in this set must be orthogonal. That means the dot product must be 0. That's the problem, right? And what's the solution? We don't know. We're going to learn later, right? Yeah, that's the magic. There's a magic formula to convert every set of vectors to a set of orthogonal vectors. Now, it sounds crazy, but it's actually very beautiful and geometrically reasonable. You can do it. If you would have done the same thing, probably, if you think about it hard enough after having the intuition about the problem. And it will, not this lecture, the next lecture we're going to talk about QR factorization. That's one of the most amazing factorization. It will come out of this process. It is unbelievably useful. It's called QR factorization. All right, the orthonormal vectors are linearly independent. That is just the fact that it is possible to prove. Because they are, we already talked about it. They're orthogonal. They're pointing to independent directions in the space. They have nothing in common, right? So it will not be possible to write one of them as a linear combination of the other ones. So I think this intuition is enough to accept the fact that a set of orthonormal vectors are linearly independent. Now, a set of orthogonal vectors, if we want to be really precise with the language, a set of orthogonal vectors are linearly independent if none of them is the 0 vector. Just to be precise, because if they're orthogonal and not normalized, we have the option of having 0 vectors. Then that will change the problem. But being orthonormal means the norm is 1, and because the norm is 1, that means it's not the 0 vector. So it is understood by orthonormality of the set of vectors. So you might imagine that you have a bunch of vectors, it's a very high dimensional space. Sounds like a nice way to work with them, right? Independent directions. That's feels like a natural way to work with directions. What about matrices? We talked about vectors, a set of vectors. It turns out we can generalize this to rectangular matrices too. Why? Because I just gave you a hint earlier that the dot product was actually showing up in the matrix product, right? So the notion of orthogonality for vectors, it can be extended to columns or rows of matrices because those are just vectors. So the set of vectors we have in the rows of a matrix and the set of vectors we have in the columns of the matrix can be an orthogonal or orthonormal set of vectors. So we say an n by m rectangular matrix Q is orthonormal if Q is a tall matrix, tall like this, tall means more rows than columns for matrices. Its columns are orthonormal vectors, and that's equivalent to writing that Q transpose Q equals the identity matrix of size m. So Q was n by m, therefore Q transpose will be m by n. So we get m by m identity matrix. So we always go with the smaller one, right? N and m, whichever is the smallest, this will be the result of, we write it in a way that the identity is from the smaller size. You can talk about the other way. If Q is a wide matrix, that means it has more columns than rows. Then we talk about rows, the smaller number again. Its rows are orthonormal, and that's equivalent of writing Q times Q transpose equals the identity matrix of size n. This time n is smaller than m. So you can have the notion for columns and rows, because why not? You can think about columns as vectors, rows as vectors. Right? Go ahead.
Is that Q transpose times Q is the identity matrix as the definition for linear independence as well?
The question is, can we use the definition of Q transpose times Q equals the identity matrix as the definition of linear independence? We can, but this is like an overkill because for a set of vectors, it is not the most minimal. It's not the minimal definition, right? For a set of vectors to be linearly independent, they don't have to be orthonormal. But it is true that if you have Q transpose Q equals the identity matrix, the columns are orthonormal, or form an orthonormal set of vectors, and we had a fact that we know that they are linearly independent, right? I think the other way is an overkill. So you might guess that we're going to see something cool. What if n equals m? What happens if n equals m? Yeah. So Ben is pointing out that if Q is a square matrix, n equals m, Sounds like we're going to have both columns and rows to form an orthonormal set. So it becomes very special. And in fact, we get n by n matrix, and then you have Q transpose Q equals the identity. And we get Q times Q transpose equals the identity. And by definition of the inverse of a matrix, we learned that because Q transpose times Q, both from left and right, will result in the identity matrix, then therefore, the inverse of Q must be its transpose. This was the definition of the inverse of a matrix. And we proved that it's unique. So this is very interesting, and you will see that this is extremely useful next time when we talk about solving a system of linear equations using QR factorization, that the inverse of we actually don't need the inverse for a system equation. Forget about that. But it is very useful that the inverse of Q is Q transpose. It's very easy to compute. Forget about a linear system. We can do it for rectangular. I thought about the square systems for a moment. So this is really cool. Inverse equals transpose. You might remember we had this for what class of matrices? Permutation matrices had this property, right? So you might get, this gives you a hint that they're related. Now you can go back and think about permutation matrices in a different way. They're columns, they're rows. Are they orthonormal? Are they orthogonal? Now suddenly you're thinking about their angles in space. These columns that we had to permute rows. Now it is very interesting. You can talk about it just a lecture on the permutation matrices and their orthogonality and what it means in space doing that. But I'll leave that for you to think about it. Remark. For a square matrix, it is true that Q transpose Q equals identity of size n. Also, Q times Q transpose equals the identity matrix of size n. And therefore, so we have if and only if, Q inverse equals Q transpose. Now, this is not true for our tall and wide matrices because it doesn't work both ways. If you have, for a tall matrix, you have more rows than columns. Therefore, then, we go with the smaller number, columns. For a wide matrix, we go, again, with a smaller matrix, which is n. Now, is it? Yeah, n. Now, this actually goes back to the question you had, Ben, that can I have more orthogonal vectors than the dimension of the space? And the answer is no. Right? So this might be related to that. You can imagine that if my matrix is, let's say, I don't know, 4 by 2, right? I cannot have 4 orthogonal vectors in a 2D space. So I'm going to go with the smaller one, too. And vice versa for the wide matrix. So that was a really good question related to this remark. What happened? Huh? Something is telling us to end the lecture. All right, now let's go back to the problem. I give you a set of vectors. This is the last topic. I give you a set of vectors, u1 to um. They are linearly independent. And I want to generate an orthonormal set of vectors, orthogonal set of vectors. So the process of doing that is called Gram-Schmidt, I mentioned before. And here is the idea. U is the original set of vectors. V is the output, the result. Set the first one, V1 to U1. This is easy. That means pick the first direction to be the same that it is. That's my first independent direction. The second time, use this magic formula that says that pick U2 and subtract something from it. And that something is the dot product of U2 and V1. V1 was the result of the previous step, the previously chosen vector as the output. Subtract something multiplied by V1. Now, U2, we know it's already linearly independent of V1 or U1 because that was the given condition. And something multiplied by it. Now, you already know that this is going to be, ultimately is going to be a number because the dot product will give you a number. Now, dot product of two vectors divided by the dot product of the two other vectors, which is the same vector, V1 and V1. Ultimately, it will be a number. So this is telling us that U2 minus some factor times V1 will give you V2, and V2, this is such that by construction, V2 will be orthogonal to V1. All right? This Gram-Schmidt process is telling us that. Then you might ask, how is this even possible? What is this magic alpha that if I multiply it by the previous direction and subtract it from my second vector, make the result independent, orthogonal to the previous one? Now I'm going to explain this, because if you understand this, then we just keep doing the same thing. Now imagine you have a vector here and another vector here. Call this V1. This is U2. Maybe this is a better color. Now, I think we can agree that if I take an orthogonal line, right, to this vector, I can decompose my vector U2 to something that I'm going to call it V2, and another vector, what should we call it? I don't know, U bar 2, some symbol. Now, do you agree that U2, as a vector, it is a sum of these two vectors, because I can just follow these two vectors, right, in a space and get my vector. So the idea is that given a vector, I know this vector is spanning this line. The first vector v is just a line, because any scalar multiple of that will be along that direction in the space. I can go to any point on that line. The vector spans that line. Now, the natural question is that what is the overlap in the direction, what is the overlap in my U2 with this vector V1? If I manage to subtract that direction from U2, what's left must be independent in terms of direction in space, therefore orthogonal, right? So this idea makes sense, and it will be true in any dimension. The problem is, how can I project it orthogonally into this direction, right? And here comes the power of dot product. So the dot product, what it's doing is actually giving you the magnitude of a vector along another vector. So what dot product is measuring is the magnitude of a vector along another vector. So the norm was, in a sense, it was the magnitude of the vector along itself. Same direction, right? Because these vectors are also pointing in different directions, you can ask yourself, what is the strength of my vector in each direction of space? And the dot product is giving you that. So this U bar 2, it is in fact the dot product of U2 vector by V1. This will be the magnitude of U2 along V1. Now, this is not good enough because this is just a number, right? It's just a magnitude. I need to turn it into this vector so that I can subtract it from the original vector. And to do that, that's why we have this formula. Now, instead of V, I'm also interested in the direction, because the magnitude of V can change the scale of this vector, right? I do not want to change the scale. I just want to project it in this direction, whatever is the magnitude of U in that direction. And that leads to this idea. I'm trying to informally convince you, right? But you can, using geometry, but you can prove it in different ways. So I normalize V1 to get a direction, and then I calculate the dot product of U2 with this normalized vector. This will be a number, right? This will be my, say, it's not consistent with that alpha, but it's a number. Then I multiply it by, again, a vector along V1, a unit vector, to turn it into U bar 2. I constructed U bar 2 with this idea. Now, it is sufficient to subtract it from U2. Then I get rid of whatever is in my vector U2 along V1. And that will result into the desired outcome, which is V2, orthogonal. Now, I expect this idea of projection makes you a little uncomfortable. You probably want to think about it and ask your questions. Try to internalize this idea by thinking about it, and there will be an example. You should go through the example and solve it. That will help. But this is an intuitive way why Gram-Schmidt process works. Where does the formula come from? So, the term, the dot product of u and v divided by the dot product of v by itself times v, it is in fact, well, this part is just norm squared. It is in fact related to this idea that take the magnitude of my vector u along the direction of vector v and multiply it by that direction to create u bar 2. That's what it's doing. Now you could call this normalized vector E, some unit vector. You can write it differently, substitute E. So you form a unit vector along V, take the dot product of V with that unit vector to know the magnitude of your vector along that direction. This will be a number, scalar. So to turn it into vector in that direction, multiplied by E again. Then subtract it from the original vector to remove that direction. That will be a vector rejection of that vector u2 along v1. So, going back to Gram-Schmidt, the intuitive idea is what I drew there. Please go through it and let me know your questions. So the second time when I do that, I end up with v2, orthogonal to v1. And by the way, each time I can normalize my vector. When I get v1, v2, that will give me e1, e2. Along the way, I can normalize them as well. Third time, I start from the previous one. Now, it's not enough to make v3 to be orthogonal to v2. I want v3 to be orthogonal to v2 and v1, all the previous vectors. Because by definition, a set of orthogonal vectors, every pair of them must be orthogonal. So for u2, I do the same process with v1 and with v2, okay? And again, e3 will be v3 divided by its norm. So I can repeat this process, and that will give me a general formula that at a step k, I'm going to subtract this overlap part for all the previous vectors from 1 up to k minus 1. And when I do that, it will end up being geometrically orthogonal to all the previous vectors. So this will give me a general step, and I can get my normalized vector as well. Now, I'm calling them E1 and E2, but they don't have to be the columns of identity matrix here, right? These can be completely different direction in space, not necessarily what you imagine as the columns of the identity matrix, but they are going to be orthonormal. So I think personally this idea might be one of the most challenging topics, but it's also very beautiful geometrically. So please, again, take a look at how I explained it and read the book, and let's keep it a conversation, ask the questions, make sure you can internalize the idea, at least intuitively, why this works. Because then you will be very comfortable. You will use Julia, of course. You're not going to do it by hand. But no matter how many vectors you have, thousands of vectors, you know what's going on inside. You're making 1,000 vectors maybe to be orthogonal to each other in a very high dimensional space. So the set of vectors V1 to Vm as the outcome of the output of the Gram-Schmidt process are orthogonal. That means after that process that I tried to explain it using a figure, but you can show that algebraically every pair of them, their dot product is 0. Okay? Now, what is interesting is that the span of this new set of vectors, V1 to Vk, it is exactly the same as the span of the original set of vectors, U1 to Uk. Why? There's a mini proof in the book, but the intuition I can give you is that we did nothing but linear combination of these vectors, right, to subtract common direction. By definition of the span, if it does include all the linear combinations of the vector. So as long as we use linear combination to make them orthogonal, in principle, we should not change the span of the set of new vectors. They're the same. It's just a different set of vectors. We just did linear combinations. Using the dot product, the inner product that we learned today. That really enabled us to build this algorithm. And these are linearly independent because the span did not change, and the original set of vectors that we were given, they're supposed to be linearly independent. Now, you know why they must be linearly independent, because at some point, what's going to happen is that let's say V1 and U2 are the same direction, right? Then all they have is in common. Or my U1 is constructed by linear combination of multiple vectors. When I subtract the common directions, then it ends up being nothing, 0. So that's the problem. So we need the original set of vectors to be linearly independent. Now, as a byproduct of that process, each time I normalize the new vectors, so the set V1 to Vm was orthogonal, but the set E1 to Em form an orthonormal set of vectors. In the next lecture, what we're going to do, we're going to put this E1, E2, Em to be the columns of a matrix. So we apply Gram-Schmidt on the columns of a matrix. We make the column space of a matrix to be constructed from a set of orthonormal vectors. And that leads to a very beautiful factorization called QR. Q is constructed by the Gram-Schmidt process. So Q is an orthonormal matrix. R will be an upper triangular matrix, just like what you had in LU, or LDLT, more closely. If A is a square, it will be the same exactly, but in any case. And then we're going to see how to solve linear systems using this, which you might already guess. If you have AX equals B, QRX B. Now, you already know that if you multiply both sides by Q transpose Q is identity. So that leads to Rx equals Q transpose B. We're going to cover it next time. So you only need to solve one back substitution. Instead of forward, backward, we only do one back substitution. It's very convenient. Now, this was the vanilla version. That was the original Gram-Schmidt. In the lab session, Jesse will tell you probably a small modification of that. It doesn't make sense I talk about it now. You need to code it and reflect that in your code. That will make it numerically stable. This process that we just described is an ideal case. It might lead, because of the rounding error in computers, it might lead to a set of vectors that are not perfectly orthogonal, right? A tiny difference, it might end up a set of vectors that are not orthogonal. So we have a version of it that's called modified Gram-Schmidt. Usually when you use libraries, that's what they do. They don't use the original one. But in any case, they will give you Q and R. That's a QR factorization. We talk about it next time. So that's all for today. What we learned is inner product, orthonormal vectors, orthogonal vectors, and the Gram-Schmidt process to generate a set of orthonormal vectors from a given set of linearly independent vectors. Now, please go through example 9.17 in the book. There's an example with 3D vectors. It goes through the Gram-Schmidt process. Try to make sense of it both visually and, because it's 3D, you can do that, and based on the algorithms. It is very useful to visualize your vectors before and after and see if they're actually orthogonal. Because you have 3 vectors, you can do that. So that's all for today. Do you have any questions before we end the lecture? No? So QR is our first choice for in robotic mapping in SLAM, or structure from motion using cameras. We use QR factorization to do scene reconstruction. It's the best one that we use. And particularly, this one is very useful to do it incrementally. You can update it incrementally as you collect new data. We don't talk about it here, but in the grad course, I talk about how these Q related to rotation matrices and reflection matrices. Well, thanks for joining the lecture, and I'll see you next week. So Monday, I think it's the study break, right? Right. So we're going to take a break from each other so you can recover. Yeah, Monday and Tuesday are break, so take some rest to recover. But you can use Piazza. We will probably be responsive. Thank you. I'm going to end the Zoom session.